Hello students, welcome back for another pre-lab video. Callan Bentley here. This week we are talking about waves, currents, and tides. Waves are one of the most prominent features we see when we go to the beach. Those waves are a function of the energy imparted to water by wind. And that wind basically moves the top of the water the most, and that effect decreases with increasing depth. The distance from one wave to the next is referred to as the wavelength, whereas the wave height is the distance basically between the top of the wave, or the crest, and the bottom of the wave, or the trough. The wave period is how many wave crests pass a given point in a certain amount of time. Also notice this pattern of decreasing circle size as we go toward greater depths here. That's showing us the actual motion of the water. And it's basically a circular path. So when you see a wave coming towards you, that's not actually single particles of water moving from some distant point toward you. Instead, the individual particles of water basically are following a circular path, but that effect becomes diminished with greater depth. And at a depth that is about half of the wavelength, so in other words, this distance here is about half of this distance here, that effect is negligible. So you may have experienced this if you've ever been at the beach and you're about to get clobbered by an incoming wave. You dive underneath it where the wave energy is much less. Now that gets complicated when we get in close to shore because the depth to the bottom of the water is less than that 1/2 wavelength depth, which means that the waves begin to feel bottom. They experience drag along the bottom, and the top keeps moving at a relatively high velocity, and so the overall wave kind of tips over. That is what gives us the surf zone where breakers form. The velocity of a wave can be calculated from measuring the wavelength and then dividing it by the wave period. Abbreviated, that equation is V equals L divided by T, and you'll be asked to make some calculations based on that formula in class this week. Another thing you'll consider is what the effect is when incoming waves interact with an irregular coastline. Remember, waves slow down where they're shallow and they move at their full rate of speed when they are in deeper water. So that means that when you have an irregular coastline, you end up getting the wave fronts curving around that coastline. And this is called wave refraction. If you have a headland like this one that is prominently pointing out into the sea here, that means that the waves will essentially curve around and focus their energy on that headland. That means that there's lower energy in the adjacent areas, and so sediment can pile up in those sites, making beaches. Here's an example of that on a rocky headland, and you can see how the wave fronts wrap around that headland, and the wave paths are shown by the red arrows. Now there's an additional aspect of wave motion that's worth knowing, and that's the idea of the longshore current. As a wave comes into a beach at a slight angle, it pushes particles of sediment up the beach at that same angle. As the wave drains out going downhill, those particles then take a different path back into the surf, and that basically brings them directly downhill. The next wave pushes them uphill at an angle, gravity pulls them downhill, uphill at an angle, downhill, and so on. So there's an overall net movement in this case parallel to the shore. That's called the longshore current, and it moves sediment in a process called beach drift. Coastlines in some regions of the world are sinking down relative to sea level, or else sea level is rising and flooding those coastlines. In other places, the coastline is popping up relative to sea level. And there are a bunch of different factors here, including the beginning and end of glaciation, tectonic forces, and also simply the effects of sea level rise or fall. So here in this picture, we see two examples of what's called a submergent coastline. And you can see that the river valleys here have been flooded by sea level rise. In the first example here, the coastline is relatively low relief, and you can see that longshore currents basically have given us some of these nice features such as bay mouth bars, spits, and then barrier islands. On a more rocky coastline, we see that we have various features including offshore islands, wave-cut cliffs, and those wave-cut cliffs are going to be something that we also see in the other situation, which is an emergent coastline. Here's an example of an emergent coastline, and you can see some nice examples of wave-cut cliffs, like right there, for instance. You've got offshore islands known as sea stacks. You've got wave-cut platforms, and then elevated wave-cut platforms known as marine terraces. When you put these two together, the longshore current and then these different landscape features that we expect to find along the shoreline, you might expect a hypothetical shoreline to evolve over time, like is shown in these pictures. We start off with a bay, an island, and a sea arch, and then as time goes by, the sea arch is broken down, separating the pedestal of the arch from the mainland, making a sea stack. A wave-cut cliff forms. We might have sediment deposited between the island and the mainland. That's called a tombolo. Longshore current is building out a spit over on the left. That spit may seal that bay off entirely from the ocean. That makes a bay mouth bar. You can see we've got a new wave-cut cliff developed here, and the spit is developing further along the coast. Another aspect of this week's laboratory will have you investigating oceanic currents. You're going to be asked to identify and name the various major currents shown on this map. You're also going to be asked to examine currents from a sideways perspective, so not a map view, but instead a cross-sectional view of an ocean basin, in this case the Atlantic Ocean, and then come up with some ideas about why the ocean water is moving in the way that it is. This diagram basically combines those two perspectives and shows how ocean water is moving in a very general sense throughout the world ocean. This is sometimes called the oceanic conveyor belt, and it relates the surface flow of relatively warm water to the deep water, which is relatively cold but still moving at depth. Finally, you'll consider this week in lab tides. This is a look at some of the changing tides in the Bay of Fundy. Tides are where the ocean water basically goes up and down at a coastal spot over the course of a day. Tides are caused by gravity. Both the moon and the sun exert a gravitational tug on Earth's water, as well as, of course, the Earth. When the moon and the sun line up in the same direction, that gives us what's called a spring tide. It's the highest of high tides, which is a combination between the solar effect and the lunar effect. However, at other times of the month, when the moon's direction is 90 degrees to the sun's direction, the effect of the moon and the effect of the sun tend to cancel one another out, and you have a diminished amount of high tide and low tide. The pattern that we observe with respect to tides varies along the coast. The shape of the coastline, the configuration of the ocean basin, and the water depth, all those can significantly influence the pattern of tides that we see. Bottom line is this: some regions basically show one high tide a day, other regions show 2 high tides a day, and then other regions show a mixed signal. Good luck evaluating waves, currents, and tides this week in lab, and I'll see you next week.